Let's talk a little bit about beta decay. We're not going to go in and calculate beta decay energies. They're a little bit more complex, but this is the full beta decay. This is a beta, an ordinary beta. This is a beta plus, so beta minus, right? That's really an electron, right? Okay, this is an antimatter electron, a positron, right? Okay. Notice that charge is conserved. So on this side, we created a negative charge, and then one of the protons, one of the neutrons basically turned into a proton is the net effect of this, right? So we didn't change our nucleon number here. This stayed the same, right? But one of the neutrons crossed the aisle, so that we created +1, and then we created -1, right? Okay, and then the question is, what's this thing here? Okay, well, those guys are neutrinos. Here's the way it goes: is that when you look at this energy, this beta particle very rarely had enough energy to account for the mass difference between this, right? And so either energy was not being conserved in this reaction, like long scale. We're not talking about like quantum tunneling or short periods of time, right? Either energy was not conserved, or there was a very hard to detect particle that was carrying away some of the energy, right? And so we decided that our physicists decided it was much better to have an undetected particle than to totally get rid of conservation of energy. And so indeed, these have been confirmed to exist. And it's actually fairly recently that we've actually detected neutrinos, but they've been confirmed indirectly by other experiments. This is a beta plus. Notice that here the charge goes down because this goes down by 1. Because that's a positive charge like that, right? Okay. Notice also these are electron neutrinos. There's 3 different kinds of neutrinos, but these are electron neutrinos. And you're supposed to know, according to IB, that a beta minus gives off an anti-electron neutrino, and a beta plus gives off a regular matter electron neutrino. And the reason for this has to do with something called conservation of lepton number. And that is, electrons and their neutrinos are leptons. And there's actually 3 of these guys. There's a muon and a tau particle that are all leptons. We're not going to get into particle physics, but they all have their sort of mini-me that comes around with them, the neutrino, right? These guys, this has a positive lepton number, that has a negative lepton number. So the total number of leptons in the universe remains unchanged, +1, -1, right? Here, this guy, an antimatter lepton, has a -1 lepton number. That has a +1 lepton number. So again, we haven't created any leptonness, Okay, it's a weird thing. Particle physics is weird, but it all works, okay? So these are our beta decays, right? We've talked about conservation of charge. Beta minus it's just basically a beta minus. This guy is an electron. It's as if a neutron turns into a proton and an electron, okay? And then a beta plus is a positron. It's as if a proton, you can think of it this way, it's not what's really going on. A proton turns into a neutron and a positron. Positron being an antimatter electron, okay? This is an important thing. Understand that these particles are created by the nucleus. The nucleus creates them, spits them out. It's not like, we're not talking about ionization here. When an electron flies off in a beta decay, we're not ionizing the atom, right? We're actually creating something out of pure energy from the nucleus, which is weird, right? And then the neutrino is just sort of a fudge factor. They decided that the neutrinos must be carrying off the energy that's missing, right? And then this is an interesting thing, is that alpha energies are discrete. They have a particular energy that they have, and they all have that particular energy. And gamma energies are also discrete. But beta energies are continuous, and that's because the neutrino is getting a random share of the energy. And I'm not sure, I think it is just truly random how much energy this gets versus this, right? So we can subtract the mass of these guys, right, and do a same calculation we did with alpha decay, and figure out how much total energy is released in the reaction. But that energy is shared randomly between these two. So you cannot predict exactly what the energy of these betas are. You can predict the maximum energy they have, right? They can't have an energy bigger than this, but you can't predict what it's going to be. Just a little bit of history here. This is Wolfgang Pauli, and this is Enrico Fermi. And the history went something like this, right? The beta decay products were missing energy. Pauli proposes a particle that is carrying away energy, and Enrico Fermi names it neutrino. This is Italian for little neutral one, right? Ino means little, and neutral means neutral, right? Okay. And basically in 1956, when particle accelerator experiments confirmed the existence of neutrinos, nobody was surprised by this. Okay. Nobody was surprised that indeed these particles did exist. Okay. Recently, not too recently, but this is the particle detector that detected them. This is a tank full of water, and this thing is deep, deep in a mountain in Japan, right? And this is thousands of photomultiplier tubes. These are very, very sensitive light detectors, right? And then there, you can see where it is down deep in a mountain like that, right? This is called the Super K. And we detected neutrinos, and the way we detected them was by looking at Trankov radiation. And Trankov radiation is this crazy stuff, right? An electron neutrino can interact, and right now there's just bajillions of these neutrinos going through your body all the time, but they don't interact with matter, which is a good thing, just because if they did, why, we would die. Okay, but these neutrinos, when they go through that tank of water, since there's so much water and there's so many electrons in there, right? Eventually, one neutrino randomly is going to interact with an electron. Now, what it can do is it can make the electron go faster than the speed of light in water. Now, the speed of light in water is slower than the speed of light, correct? So it is possible to go faster than the speed of light in water, yet still be going slower than the speed of light, correct? Yes? Okay, so basically you're going between the speed of light in water and the speed of light. Now, when you go faster than the speed of light in water, you give off this thing called Trankov radiation, which is like a sonic boom, okay? It's like a sonic boom, only it's a lightic boom. You give off this like shock wave of light, and that light has a particular signature to it, okay? And so those detectors on the walls of this thing can detect that little sonic boom of electrons going faster than the speed of light. The only thing that could make them go faster would be a neutrino. Pretty cool, huh? So we have detected them. We do believe that they have rest mass too, so that's kind of a cool thing. Rest mass means that even if they're not moving, they have mass.